There is no doubt about it. Solar flares and coronal mass ejections, or CMEs, are very, very exciting. While they pose no direct threat to people down on the ground, these flashes of X-ray energy are often larger than the Earth itself and can create excited states in Earth's atmosphere. Beyond just giving us light, the solar energy always creates a bit of excitement in the atmosphere above the spot on Earth where it is noon at that time, or where the sun is directly overhead. During quiet solar activity, the influence on Earth's atmosphere is at its weakest and has very little effect. But during strong solar flares, the area of Earth that is facing the sun is bathed in extreme ultraviolet and X-ray radiation, which can excite the part of the atmosphere used to help send radio signals across the world, and causing what is known as a radio blackout. They occur very quickly upon the occurrence of the flare because that energy moves at the speed of light, and likewise, the blackout subsides when the flare does. Well, what causes solar flares? The energetic release occurs as the plasma and charged particles controlled by the magnetic field loops coming out of sunspots interact, and while the sunspots are moving and shifting around, so are the loops. When these fields interact such that you have fast-moving plasma changing direction and/or accelerated to near the speed of light, we can measure X-ray energy, or the solar flare, and we use GOES-15 satellite to do so. The GOES-15 is a predecessor of the GOES-R that will launch in 2016, and the scale on which we measure solar flares, from lowest to highest, goes A, B, C, M, and X. For the purposes of space weather, solar flares begin to become significant in the higher C flare range, but the largest flares, M, and especially X-class solar flares, are likely to create coronal mass ejections. The same energy that sends the matter way up into the corona in those loops, the same energy that keeps those billion-ton plasma filaments floating above the surface, is highly surged in a solar flare. Much of the material can be ejected out into space. The sunspots themselves are often bigger than the Earth, so consider just how big these eruptions can be. Solar flares are not the only makers of CMEs. Those plasma filaments that hover above the surface can release as well. And these usually do not have a flare that happens first. They simply erupt. Two special cameras aboard the SOHO satellite, known as the LASCO C2 and LASCO C3, are made super sensitive to the charged particles that eject from the sun. They have to cover up the sun with a central disk because it's so sensitive. Otherwise, the glare and brightness from our star would not allow us to see the expanding clouds of particles as they leave the sun. For another idea of the size of things, look at how big these clouds get as they leave the sun. Within hours of the eruption, the cloud can be big enough to hold multiple suns. These images allow us to determine the direction the CME is heading and often just how much material has been ejected. This is important because these clouds of particles are the primary thing that changes the solar wind, or what we call space weather, especially in an Earth-directed CME, which can intensify the solar wind to the point it creates the auroras. And if the flare is big enough, the CME is big enough, it can do a lot more than that.